Welcome! In this session, we'll tackle an interesting graph theory problem, finding the center of a star graph. This is a straightforward yet important problem that tests your understanding of graph structures and efficient algorithms. Let's dive in. In this problem, we are working with a specific type of graph called a star graph. A star graph consists of n nodes, where one central node is directly connected to all other n1 nodes, and there are no connections between the non-central nodes. This unique structure means that the center node has the highest number of connections, making it distinguishable from all other nodes. The task is to identify this center node given the edges of the graph. The input is a 2D array edges of size n1, where each subarray, u, v, represents an undirected edge between nodes u and v. The output will be a single integer representing the center node of the graph. The problem ensures that the graph provided is always a valid star graph, so there will always be exactly one node connected to all others. Let's look at an example to better understand the problem. Suppose we are given the input edges equals 1, 2, 2, 3, 4, 2. These edges describe a graph where node 1 is connected to node 2 is connected to nodes 1, 3, and 4, and node 4 is connected to node 2. In this graph, node 2 is the only node that connects directly to all other nodes, making it the center of the star graph. Therefore, the output in this case would be 2. This example illustrates how the center node can be identified by observing which node appears in multiple edges and connects to all others. Here's another example. If the input is edges equals 1, 2, 5, 1, 1, 3, 1, 4, the graph described by these edges has node 1 connected to nodes 2, 3, 4, and 5. The other nodes 2, 3, 4, and 5 are only connected to node 1 and not to each other. This makes node 1 the clear center of the star graph, as it is the only node with direct connections to all other nodes. The output for this example would be 1. These examples demonstrate the pattern of identifying the center node by analyzing the connections in the graph. Let's consider a few important edge cases. First, in the smallest star graph, such as edges equals 1, 2, 1, 3, there are only 3 nodes. Here, node 1 is the center since it connects to both other nodes, and the output is 1. Another edge case is when node labels are non-sequential, like edges equals 10, 20, 30, 10, 10, 40. Even though the labels aren't consecutive, node 10 is still the center as it connects to all other nodes, so the output is 10. Finally, for large inputs, where the graph has up to 10⁵ edges, it's important to ensure the solution handles this efficiently. For example, if all edges connect to the same node, the algorithm must still correctly identify the center without being slowed down by the size of the input. These cases highlight the need for a robust and efficient solution. To solve the problem of finding the center of a star graph, we first need to fully understand its structure. In a star graph, there is exactly one central node that connects directly to all other nodes, and none of the outer nodes connect to each other. Our goal is to identify this central node using only the edges provided. One way to approach this is through a brute force method by counting the degree of each node. The intuition here is that the center node will have the highest degree since it connects to all other nodes. To implement this, we first create a dictionary to track the degree count for each node. Then, we iterate through all the edges, incrementing the degree for both nodes in each edge. Finally, the node with the highest degree is identified as the center. While this approach works, it has some trade-offs. It requires additional memory to store the degree counts, and although the time complexity is linear at O(n), it is not the most efficient solution available. A more efficient method leverages the unique structure of the star graph to drastically simplify the process. Instead of counting degrees for all nodes, we can identify the center directly from the first 2 edges of the graph. The key insight here is that in a star graph, the center node appears in every edge. This means that if we look at the first edge, the center must be one of the 2 nodes in it. To confirm which one, we simply check if either of these nodes also appears in the second edge. If the first node from the initial edge is present in the second edge, that node is the center. Otherwise, the second node from the first edge is the center. This approach is highly optimized because it avoids unnecessary computation and additional memory usage. Its time complexity is constant, O(1), since we only check the first 2 edges, and it does not require any extra space. The trade-off is that this method assumes the input is always a valid star graph, so no additional validation is performed. Given the two approaches, the optimized method clearly stands out as the better choice. It is simple, efficient, and does not require any extra space. By directly leveraging the unique structure of the star graph, we can identify the center node with minimal computation. While the brute force method is easier to conceptualize, its higher space usage and unnecessary iteration make it less desirable. The optimized approach is particularly well suited to this problem, as the constraints guarantee that the graph will always be a valid star graph. The key observation that the center node appears in every edge allows us to focus solely on the first two edges, achieving constant time complexity. The final algorithm is both elegant and efficient. In Python, we extract the nodes from the first edge, then check these nodes against the second edge to determine the center. This ensures we solve the problem with optimal performance and minimal overhead. In this problem, we're tasked with identifying the center of a star graph. A star graph is a special type of graph where one central node is connected to all other nodes, and the remaining nodes have no direct connections with each other. The input is given as a list of edges, where each edge is represented as a pair of integers, u, v. Our goal is to determine which node is the center, based on these edges. To break this down, consider that in a star graph with n nodes, there are exactly n1 edges. The center node is the only node that appears in all the edges because it is directly connected to all other nodes. Meanwhile, all other nodes appear in exactly one edge, as they are only connected to the center. For example, if the input edges are 1, 2, 2, 3, 4, 2, you can observe that node 2 appears in every edge. This tells us that 2 is the center of the graph. With this understanding, we can now explore ways to solve the problem efficiently. One way to solve this problem is by using a brute force approach that counts the frequency of each node. First, we use a hash map, or dictionary, to count how many times each node appears in the edge list. For example, given the input 1, 2, 2, 3, 4, 2, we iterate through the edges and count occurrences. Here, node 1 appears once, node 2 appears 3 times, node 3 appears once, and node 4 appears once. Once we have the frequency counts, we simply find the node with the highest count. In this case, node 2 has the highest frequency, so it is the center. This approach works because the center node in a star graph is always the one connected to all other nodes, meaning it will have the highest frequency in the edge list. After calculating the frequencies, we return the node with the maximum count as the center. An optimized solution takes advantage of the fact that the center of a star graph must appear in every edge. Instead of counting frequencies for all nodes, we can focus on just the first two edges to determine the center. For example, if the input is 1, 2, 2, 3, 4, 2, we examine the first edge, 1, 2, and the second edge, 2, 3. From these two edges, we see that node 2 is common. Since the center is guaranteed to appear in every edge, this early comparison is sufficient to identify the center. This approach significantly reduces computation time, as we don't need to process all edges or count frequencies. If the first two edges do not share a common node, which is highly unlikely in a valid star graph, we can examine subsequent edges. This method provides an optimized solution with O(1) time complexity in many cases. The key insight here is that the center node is the only node connected to all others, so it must be part of the first two edges. To implement these solutions effectively, we can use different data structures. For the brute force approach, a hash map, or dictionary, is used to store the frequency of each node. This data structure allows for O(1) average time complexity for both insertions and lookups, making it efficient for counting node occurrences. On the other hand, the optimized solution requires no additional data structures beyond a simple array for storing the edges. By focusing only on the first two edges, this approach saves both space and time. Let's apply these methods to the input 1, 2, 2, 3, 4, 2. Using the brute force approach, we first count the occurrences of each node. Node 1 occurs once, node 2 occurs 3 times, and nodes 3 and 4 each occur once. The node with the maximum frequency, 2, is returned as the center. This demonstrates how the hash map approach works step by step. Using the optimized approach, we compare the first two edges to find the center. For the input 1, 2, 2, 3, 4, 2, the first edges 1, 2, and the second edge is 2, 3. The common node between these two edges is 2, so we return 2 as the center. Let's analyze the complexity of these approaches. The brute force method has a time complexity of O, n, where n is the number of edges, as we need to count the frequency for all nodes. Its space complexity is O, n, as well, due to the hash map used for storing frequencies. In contrast, the optimized approach has a time complexity of O1, since we only compare the first two edges, and a space complexity of O1, as no additional data structures are used. This makes the optimized solution highly efficient for cases where we know the input is a valid star graph. Both methods are effective, but the choice depends on the problem constraints and guarantees. To solve the problem of finding the center of a star graph, we leverage the property that the center node will appear in every edge. Instead of iterating through all edges, we can determine the center by examining just the first two edges. The find center method begins by unpacking the nodes from the first two edges into variables a, b, from the first edge, and c, d, from the second edge. Since the center must be shared between these edges, we simply check if a is equal to either c or d. If it is, then a is the center of the graph. Otherwise, it must be b. This approach ensures a minimal number of operations and avoids unnecessary loops. This solution is efficient with a time complexity of O1, and handles all valid star graph inputs correctly, as the problem guarantees the input follows the star graph structure. By focusing only on the first two edges, we achieve a concise and optimal implementation. This is the Java implementation of the find center of star graph problem from LeetCode. The logic mirrors the Python approach. The center node of the star graph must appear in both of the first two edges. The code extracts nodes from the first two edges and checks which node is common. Key differences include the use of Java's type declarations and array syntax. The implementation is concise while retaining clarity. To solve this problem, we start with the input edges, which are 1, 2, 2, 3. These represent the connections in the star graph. Our task is to identify the center node, which is the one common node connected to all other nodes. First, we analyze the nodes in the first two edges. From 1, 2, we take the nodes a equals 1 and b equals 2. From 2, 3, we extract c equals 2 and d equals 3. Now, to determine the center, we compare these nodes. We check if a1 matches either c, 2, or d, 3. It doesn't, so we move on to b, 2. Here, we find that b matches c because b equals c. This means that b is the common node across these edges. Therefore, the center of the star graph is node 2, and that is our output. In this example, the input edges are 4, 5, 5, 6, 5, 7. Although 3 edges are provided, we only need the first two edges to find the center. From the first edge, 4, 5, we extract a equals 4 and b equals 5. From the second edge, 5, 6, we extract c equals 5 and d equals 6. Now, we compare these nodes. First, we check if a4 matches c, 5, or d, 6. It doesn't. Then, we check b, 5. Here, we see that b matches c because b equals c. This confirms that b is the common node. Since node 5 is connected to all other nodes in the graph, it is the center of the star graph. Thus, the output is 5. Here, the input edges are 8, 9, 8, 10. Once again, our goal is to identify the center node. From the first edge, 8, 9, we extract a equals 8 and b equals 9. From the second edge, 8, 10, we extract c equals 8 and d equals 10. To find the center, we start by comparing the nodes. First, we check if a8 matches either c, 8, or d, 10. In this case, a equals c is true, so we immediately determine that a is the common node. Since we have identified a match, there's no need to check b further. The center of the star graph is node 8, and that is our final output. The time complexity of the solution to the find center of star graph problem is O1, or constant time. This is because the function only accesses the first two edges of the input list, and accessing elements in a list by index in Python is an O1 operation. After accessing these edges, the nodes are unpacked into variables, which is also a constant time operation as it involves processing a fixed number of elements. The function then performs a few conditional checks to compare the nodes, such as determining if the first node in one edge matches the first or second node in the other. These comparisons and logical operations are simple and also take constant time. Importantly, the solution does not depend on the number of edges in the graph. Whether the graph has 3 edges or a million, the function always processes exactly 2 edges, making the overall time complexity O1. The space complexity of this solution is also O1, or constant space. This is because the function uses only a small, fixed number of variables to store the nodes of the first 2 edges. Specifically, variables like A, B, C, and D are all that's needed, and this number does not increase with the size of the input. The function does not create any additional data structures, such as dictionaries or arrays, and there is no recursion or dynamic memory allocation. Furthermore, the input list of edges is passed as an argument, and the function only reads from it without copying or modifying it. These factors ensure that the memory usage remains constant, regardless of the size of the graph. Therefore, the space complexity of the solution is O1. When compared to a brute force or naive approach, this solution demonstrates its optimality. A naive approach might involve iterating through all the edges and counting how many times each node appears, perhaps using a dictionary or an array. Such an approach would have a time complexity of O(n), where n is the number of edges, and a space complexity of O(k), where k is the number of unique nodes. In contrast, the given solution takes advantage of a key property of star graphs: the center node appears in every edge. By checking only the first 2 edges, the function efficiently identifies the shared node, reducing both time and space complexity to O1. Additionally, whether the graph is small or large, the function always processes exactly 2 edges, making the best, average, and worst-case time complexity identical O1. This consistency highlights the strength of the approach. The reasoning behind the solution can be understood mathematically by considering the structure of a star graph. In a star graph, the center node is uniquely connected to every other node. This guarantees that any 2 edges will always share the center node. By examining just the first 2 edges, we can confidently identify the shared node. If the first node of one edge appears in both edges, it must be the center. Otherwise, the second node of the first edge is the center. No further processing is required, which ensures the time complexity remains constant at O1. Similarly, the space complexity stays constant because the function relies only on a fixed number of variables and does not allocate any additional memory. This reliance on the inherent properties of the star graph underpins the efficiency of the solution. When working with star graphs, there are several common mistakes to watch out for. First, it's important to remember that a star graph is always connected by definition. There's no need to check for disconnected components, as this can add unnecessary complexity and waste valuable time. Another frequent error is iterating through all nodes to count their degrees. The unique structure of a star graph means that the center has the maximum degree, which equals n1, while all other nodes have a degree of 1. By focusing on just 2 edges, you can identify the center node much more efficiently. Additionally, overcomplicating the solution by using an adjacency matrix instead of the provided edge list is a mistake. Adjacency matrices consume n² space, which can lead to memory issues for large inputs, while the edge list approach only requires n space. It's also essential to verify the input constraints. While the problem typically assumes a valid star graph, edge cases like missing or duplicate edges can occur, particularly in interview settings. Lastly, be mindful of indexing errors. Some graphs use 1-based indexing while others use 0-based, so it's critical to pay attention to the problem description to avoid incorrect results. Now, let's consider some insights that are particularly useful for interviews. The key idea here is that in a star graph, the center node connects to all other nodes, meaning it will appear in every edge. This gives us a simple way to determine the center: identify the node that appears most frequently in the edge list. An optimal approach leverages this property by focusing on just the first 2 nodes in the first edge. By counting how many times these 2 nodes appear across the edge list, you can pinpoint the center node in n time. Be prepared to handle edge cases, such as graphs with only 2 nodes, which represent the smallest possible star graph. You might also encounter edge lists with duplicate or unordered entries, or even non-standard indexing, like 1-based indices. When explaining your solution, it's important to highlight why the star graph structure allows for this efficient O(n) approach, and demonstrate an understanding of trade-offs, such as the decision to count frequencies versus traversing all nodes. This problem also connects to other related graph problems that can deepen your understanding of graph structures. For example, LeetCode 997, Find the Town Judge, is a similar problem where one node connects to all others, though it adds additional constraints. Another relevant problem is LeetCode 261, Graph Valid Tree, which involves determining if a graph forms a tree. This can help you build a stronger foundation in graph validation and connectivity. LeetCode 323, Number of Connected Components in an Undirected Graph, is another useful problem for practicing graph traversal and understanding how components are connected. Finally, LeetCode 1971, Find if Path Exists in Graph, is a simpler problem that focuses on basic graph traversal techniques, making it a good starting point for beginners who want to develop their graph problem-solving skills. There are also alternative approaches to solving the star graph problem that are worth considering. One method is frequency counting, where you use a hash map to count how often each node appears in the edge list. The node with the highest frequency is the center. This approach is straightforward but requires O(n) space for the hash map. A more efficient method is direct comparison, which involves checking only the first two edges in the edge list. The center node will be the one that appears in both edges or, more generally, in all subsequent edges. This approach is optimal in both time and space, requiring only O(1) additional space, but it does demand careful handling of edge cases. Another option is to construct an adjacency list and identify the node with the most neighbors. While less efficient than frequency counting, this method can be useful for learning about adjacency list construction and its applications in other graph problems. When choosing an approach, it's important to weigh the trade-offs. Frequency counting is intuitive but uses more space, while direct comparison is faster and more space efficient but may require more careful implementation. Great work! To recap, we solved the star graph problem by leveraging its unique structure for an efficient solution. Remember the key insights and apply them to similar challenges. Thanks for joining, like and subscribe for more tutorials. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!